Okay, we are recording. Good. Excellent. So now we're going to learn. I was like looking for the. I was looking for the ukulele. What was that? Oh, a rubber band.
A tiny one. Oh my God. I was about to burst into song if I had more of these.
So we're going to talk about stability, gain margin, and phase margin from the Bode plot, which is actually the preferred way to do this. So Bode plots are an alternative representation of the positive j omega axis Nyquist plot, which we discovered you can learn about stability from. You don't have to do the negative j omega, and you don't have to do the infinity one, so you can get away with it. For these reasons, the stability, gain margin, and phase margin can all be found from the Bode plot. In fact, this was the preferred method for finding these quantities. Well, it's at least the preferred method for finding the latter two of these, the gain margin and phase margin. Stability, this is probably on par with the root locus methods you've learned and Ralph Hurwitz and all of that. So this is just another way to do it. Gain margin and phase margin, now this is the preferred way to do that. So it is common but somewhat risky practice to simply use the Bode plot to determine stability, gain margin, and phase margin. Here's why it's risky. When we use it, we assume that the system, one, is open loop stable, and so not only is it open loop stable, and with sufficient gain, encirclements of -1 are clockwise, okay, which may not be true, and 3, the Nyquist plot has a single negative real axis crossing, which is also not always respected. So they're commonly met, but there are plenty of systems for which they are not. Okay. For this reason, we encourage caution with this common practice and proceed by describing the method. So what I would say is, since you're going to get your Bode plot from MATLAB anyways, toss in a Nyquist, make sure that these assumptions are met. And then go ahead and use the Bode plot for the gain margin and the phase margin. You can tell just based off of a quick little Nyquist plot whether or not these conditions are met. And if they aren't met, then you should use the Nyquist plot to do that. If they are met, then just go ahead and use the Bode plot. So, recall that the gain margin, GM, is defined by the distance between the negative real axis intercept of a Nyquist plot and -1. Okay? Just realized that was a typo. This occurs at -180 degrees. So if we went back to our figure here, when we have this crossing of the real axis, we're at -180 degrees, right? Because the phase is measured from the positive real axis, so -180 degrees. The distance is between the -1 and the -180 degrees. So, on a Bode plot, such as that of figure 7.7, so like, say you've got a Bode plot, and we're going to look at it in the region of 0 dB, which corresponds to magnitude what? Not in dB. Do y'all remember? 1. Yeah. 0 dB is just magnitude ratio of 1. So what is, so magnitude 1 is there, and then at negative 180 degrees is also the region that we care about as well. So we care about magnitude 1 and negative 180 degrees. This is similar to what we're looking at here, but we're not putting them on a polar plot. So the excuse me, the polar plot has magnitudes. We care about this -1 magnitude, and phase, we care about this -180 phase for the gain margin and the phase margin. So let's interpret our definitions of gain and phase margin in terms of the Bode plot. So similarly, recall that the phase margin is defined as the difference between the angle at magnitude 1, right? So magnitude 1, which is this unit circle in the Nyquist plot. So that's this point is where it crosses, right? It's the difference in angle between that ray and this negative real axis. That's the phase margin. So on a Bode plot, when the magnitude crosses 1, starts to go below 1, and it starts to get smaller and smaller, that magnitude, then we know that that this corresponds to the phase margin. So whatever frequency this occurs at, that occurs at the phase margin frequency. So what you do to find the phase margin is to locate this 0 dB crossing of the magnitude plot and just follow it straight down to whatever the corresponding frequency is. So just follow it straight down and see what the phase is there. And the distance from negative 180 degrees to there, up to there, is your phase margin. Okay? If your phase margin is negative, so if your phase is actually down here, and your phase margin has to go below 180 degrees, if it's going that way, that's negative phase margin, which means that you are unstable based on the assumptions about our system that we made. So we're using the Bode plot, so we have to check on the Nyquist that it's true. But often this is the case. So that's cool. To find the gain margin, you have to look and see where is this remember that the gain margin is defined as the logarithm of A, right? It's 10. Was it 10 logarithm A? Or 20, I can't remember. But it depends on this intercept, right? And that intercept occurs at negative 180 degrees. And so what we do is we find where this phase crosses 180 degrees, and we follow it up at the same frequency, and we find out how much of a margin here we have before we get to 0 dB, which would be this point, magnitude 1 on the negative real axis. So that's our gain margin, and we have to do it in dB. But that's, why is gain margin usually in dB? Well, because usually people think about it in terms of the Bode plot, which is in dB, and so that's why we think of it in terms of dB. So gain margin is found by just going to negative 180 degree crossing and following it up. And gain margin is defined as positive from 0 dB down to this. So if you end up with a gain margin that goes up, that's a negative gain margin, and your system is unstable. Okay? So that's gain margin and phase margin from the Bode plot, but let's not forget that we have to be careful when we apply Well, so it's super easy if we just use this, right? If we just use the Bode plot, it's really nice. And we'll do an example in a moment, and we'll see, like, in MATLAB, they'll even draw these lines for you. Like, you don't even have to do it yourself. It's so ridiculous. But MATLAB is not going to tell you if that means it's actually stable or not. It's basing that on the assumptions that we made on this previous page. 1, 2, 3, these are the gain and phase margins of your Bode plot, assuming that these hold. So you have to be the one to check that. MATLAB won't do it. At least I don't know of any way that MATLAB checks that. Okay. So let's do an example. Gain and phase margin from a Bode plot. Let the open loop transfer function gh of s be defined as follows. So we've got third order, no zeros. To determine the closed loop stability, gain margin, phase margin from the open loop Bode plot. Okay. So we probably should check the Nyquist. So let's go to MATLAB and play around, shall we? Let's to MATLAB. So I think I plotted out. I didn't show you guys the plot. So we'll go to MATLAB and we'll see it. So I think I have this plugged in there correctly. So I need to set k equal to 1. So the numerator is 1, just k, and then the denominator has s cubed plus 2s squared plus 5s plus 6. Okay, good. So let's do some cells here. And
by putting the 1 in the first set bracket, in the first angle bracket, doesn't that tell you have a 0 at 1?
it just says that, so it's just a constant. So if we were to look at cis, it's just a constant there. If we have 2 terms, then it goes up to an s term, so like a ta s plus 1. Yeah, so we just have no zeros in this one. I actually, unfortunately, have to quit MATLAB and then launch it again because I don't know why. Maybe it's Apple's problems. So that'll just take a minute to boot. So we want to look at the Nyquist plot. Well, we could interpret stability from that, but frankly, it's easier to just go to the Bode plot to do it. So let's check the Nyquist first before we use the Bode plot. That's our rough methodology. So you can use this. We're not even going to go that far yet. I'm just going to define the system first, and then let's look at Nyquist. Is that the one that is the plot? Let's do help Nyquist. Yeah, it does. I thought it did. Okay. So let's look at the Nyquist response. So there's our -1. And so first off, we had to look at we should look at our eigenvalues of our system to see how many open loops. This is the open loop GH, right? No. How many eigenvalues of this are in the right half plane to start, right? So our assumption, if we're going to use Bode plot, is that there are none, right? So we look at Eig of cis, and we see negative real part, negative real part, negative real part. So that's a check. So we've verified that. We also want to check that our Nyquist plot has two properties. First off, that for low gain, there are no encirclements. So, well, a few things. No encirclements at low gain, and that for high gain, there are clockwise encirclements. So notice that this is directed this way, right? So if we were to scale this up, we're going to eventually get -1 inside this, right? Inside this loop, which is going to have two clockwise encirclements of -1, and therefore will make the system unstable. Okay, so this is the typical system that we often see, but we didn't know that until we looked at the Nyquist plot and we checked the eigenvalues. So we did those two things, and now we know we're good to go. So,
If you're looking at that, trying to make sure it only crossed the
oh yeah,
real axis once.
thank you. That was the other thing we had to. It only crosses the negative real axis once. So the negative real axis starts here and goes left. So it only crosses it the one time. We don't have multiple crossings because you can get multiple crossings, and then you can. What happens if you have multiple crossings? You're going to cross on the Bode plot the negative 180-degree line multiple times, and you're going to cross the. I mean, depending on the situation, you're going to cross your magnitude 1, your 0 dB line multiple times. So to really interpret what's going on, it's best to just go to Nyquist and see, okay, like what do these encirclements really mean? Like, and that's the safe bet. In the Bode plot, you're kind of feeling it out in the dark, and it's best to just come back here and say, okay, I see what's going on. If we scale this up, it's going to go unstable. And I also have a pretty good idea that you could multiply this by a gain of, this is like 0.25 or something like that. So like a gain of 4 or so, and then I should go unstable, approximately. So you can scale it just like this, put in your gain at 4, and we didn't quite.
Touch the marginal.
Yeah, is it marginal here? This might be marginal. Oh my goodness, right on the money, or pretty close. It's hard to say if that's within the numerical error or what, but yeah, so if I did a gain of 9, clearly we've encircled it twice, clockwise. So our z is equal to -2, and we're unstable. So n is equal to -2, p is equal to 0, and so z is equal to -2. No, positive 2. It's negative n. There are actually a couple different standards for whatever reason. We couldn't agree on one or the other of n equals z plus p or n equals z minus p, and like the definitions change subtly. So we just can't agree on that formula. So we all just have to deal with. I think that I have it consistent with. I think I have it consistent with Nice, but Nice is somewhat unusual because a lot of other books use a different convention, which is weird, but for whatever reason, it works that way in Nice. So this is all jiving with what we're familiar with, right? So now our next step is to so we can use Bode and look at the Bode plot, right? Which is fine, but it's not something that we can see the values very easily from. We can pick out points. I will tell you that the margin one's easier to use. Oh, we should set this to gain of 1. while we do all of these calculations, right? K should be 1, and then we'll be able to see the gain margin and the phase margin properly. If you set the gain to something non-unity, then you end up with a skewed version of gain margin and phase margin. So that's important to remember. So let's look at this. The ordering of this was kind of weird. I'll move this down here. So now let's look at margin. And we see following. So the phase margin's coming out strangely, so we'll have to investigate that. The gain margin is coming out to be 12 dB. Okay? So what it does is it crosses the okay. So I'm not my gain or my magnitude never gets up to 0, right? So that's my problem. So the phase margin is not defined for this system. And that's because if you look at the Nyquist plot, it never goes outside of the unit circle, right? So the phase margin is not going to be defined because it never leaves the unit circle and then enters it before it comes in to here. But the gain margin will still be defined. It doesn't mean that the phase margin is this doesn't mean you're unstable or something. It just means it's not defined for the system, which is fine. Now your gain margin is going to be still defined, and so when we go through negative 180 degrees, which it doesn't, I thought it showed a line here, but it should show the line at negative 180 degrees, or I guess it doesn't when it doesn't give you a phase margin. But let's see, in between those 2 points, we look up here and we see how much gain we can increase before we hit 0 dB. And that's this distance. So if I put my check on there, it's between those two. So it's between negative 11 and negative 12 dB below, or negative 11 and negative 13 dB below 0. So so in other words, we have a gain margin of 12 dB. It even says the gain margin on the plot, but essentially you can move this thing up and scale it by 12 dB, which if we wanted to know what that was in amplitude, we would have to compute that, but dB is usually what it's expressed in anyways. So I said a factor of 4, and that is actually what is approximately 12 dB is. So those are sort of like different ways of hacking this or cutting this and to look at stability. But it's important to say, so it is tempting, I know, that Nyquist plots are a little weird. And why they work is a little esoteric, and it's kind of hard to follow. And there's a tendency for students to be like, oh, I get Bode plots. Nyquist is freaking me out. I'm going to focus on Bode plots because you can do the stability stuff from Bode plots, and gain margin, phase margin, and stuff. Yes, but you're going to be in trouble if you wind up with a system that doesn't jive with those assumptions that we make about it to use the Bode plot. So I find the best policy is to just look at the Nyquist plot first, get a feel for the system, make sure that it fits those criteria that we have for it, and then afterwards use the Bode plot for the gain margin and the phase margin. Especially the phase margin. Gain margin is easy enough from the Nyquist plot. It's actually not hard from the Nyquist plot, but the phase is, I mean, it's not super hard. You have to take an arctangent. I believe in you guys. I think you guys could take an arctangent. So, right, because on the so, let's say instead of putting a gain of 1 in the numerator, I put a gain of 3 in the numerator. And this gives us a gain margin, or this gives us a non-zero phase margin, okay? Because the unit circle isn't drawn on here, but I believe this leaves it and comes back into it. So when we do this one, yeah, we're going to actually see the phase margin here as well. So the gain margin and the phase margin. So the gain margin became 2.5 dB, and then we have 27 degrees of phase margin. So it's important to make sure that you kind of understand where this is coming from, and you look at it on your Bode plot. But if you look at the Nyquist plot, we could figure this out. If we also drew on top of this, they don't draw the unit circle. It would be kind of nice if they did on these Nyquist plots. For whatever reason, they don't do it. But if they drew the unit circle on here, we could find where this thing intersects it, right? Which is, I don't know, probably somewhere in here, right? So what was the phase margin in... so it's like, it should definitely not be phase margin in oh yeah, so phase margin is 27.8 degrees. So whatever that is in radians, we could essentially come here and we could click on that point that has the magnitude of 1 approximately, and then we could figure out the arctangent of that and do it too. So we could use this. When you have a tool like MATLAB, it's almost easy both ways. So the Nyquist plot is a little bit more powerful, I guess, to use. It tells you more information. Okay. Good. Any questions on finding stability from Nyquist plot, finding stability from Bode plots, making some assumptions about the system? Yeah.
The phase margin. So is that telling us? I don't exactly understand what it's telling us. How much phase we can, or how much we can change the phase until it goes unstable?
It tells you essentially how close you are to going unstable, and I'll explain it in terms of this diagram. So the phase margin makes its reference when you cross back into the unit circle. So the closer you get to crossing right at -1, which would be marginal stability, the smaller that angle is going to be. And therefore it gives you a sort of metric for how stable you are.
So is that telling you anything that the gain margin doesn't tell you?
They're related but independent quantities. It's the gain margin is a little bit easier to interpret as far as like a physical quantity, because you increase the gain and then you can either be stable or unstable. the phase also changes. The phase margin is going to decrease as you increase the gain, but it's not in that nice linear fashion. It's very nonlinear in a lot of cases. So it doesn't have quite that same tight relationship to the gain, but it is related. And if you hit that critical gain, your phase margin will be 0. And
Well, so if you know the gain margin, then if it's easy to get from here, why would you even need to know the phase margin?
so one way, so let's say that we had, so if we had a gain margin, I'm going to delete the orange one here. So say we had, I'll draw two systems with the same gain margin and with different phase margins. So this system would have the exact same gain margin as the green one. So the orange and the green would have the exact same gain margin. But the orange one would have a smaller phase margin. And it is, in fact, closer to going unstable than in a certain sense, than the green one is. So there's, and when we start doing some more controllers, you can affect gain margin and phase margin. And they're also related to other time response characteristics, which we haven't really discussed yet, but we'll discuss in the last lecture today. And so these quantities tell you things about the system that are slightly different, but they're still related. And so the time response characteristics related to the phase margin are different than that for the phase margin, or than the gain margin. And also, you can have two systems with the same, like this one, same phase margin or same gain margin and different phase margins, or same phase margins and different gain margins. And so you can sort of get a feel for the system in two different lights, although they're like not totally uncoupled. And I would say that gain margin is easily the more intuitive of the two, although they're both totally valid. And they both go to 0. Well, gain margin is usually in dB, but if you didn't have it in dB, then the gain margin would go to 0 magnitude at the same time the phase margin goes to 0 magnitude. But they approach differently, and so they have their responses are different. The characteristics of the responses are a little bit different. And we'll talk about how to interpret them a little bit in the next lecture. So I think it's the next lecture. Maybe it's this one. Now I'm forgetting. Oh yeah, no, it's the next one because we finished this one. Good. So yeah, so the last lecture, we'll talk more about the gain and phase margin in terms of the time response of the system. So yeah, did that kind of answer your question?
Okay.
Cool. I'm like at like rambling phase now, so I don't really know when I've like finished answering and when I'm just jabbering. So, what is any other questions before we move on to the last lecture? I think we're gonna get out of here on time today, like reasonably. So let's